Okay, so today we're going to talk about 6.5, which is graph of tangent functions, cotangent functions, cosecant, and secant. Oops, it's not very nice. Secant functions. And basically, this is just trying to give us a little bit of background on this. And then in 6.6, we'll kind of do a little bit of everything: sine, cosine, secant, cosecant, cotangent, tangent, a little bit of everything in chapter 6.6. So for this one, it says we have the form y equals a tangent omega x plus b, and we also have y equals a cotangent omega x plus b. I'm just going to start with tangent first because cotangent behaves almost exactly the same, but just kind of flipped around a little. And I want you to recall that y equals tan x, tangent is really sine over cosine. So the cosine is in the denominator, so that means cosine of x cannot be 0. Right? So cosine of x cannot equal 0, right? That cannot happen. So what would make cosine 0? Well, isn't cosine 0 at pi halves, at 3 pi halves, at 5 pi halves, or I'm sorry, yeah, 5 pi halves, 7 pi halves, so on and so on. So in general, what we do for cosine, for tangent, is the basic tangent function, we go from negative pi halves to pi halves. That also insinuates that the period, the period of tan x is pi. So instead of being like it normally is with sine and cosine of being 2 pi, with tangent, it's only pi. It recycles itself. The values repeat themselves after 1 pi, okay? So what we should do is we should make a little bit of a table, I guess, similar to before. Okay, 1, 2, 3, 4. Maybe I'll write this right here. Period equals pi. But if the period equals pi, then the interval size. Now the intervals aren't quite as important for this because the values aren't, the interval size is pi divided by 4. So you take pi, which is the period, and you divide it by 4, so you get pi fourths. Okay. Now the thing is we're going to start at negative pi halves this time. So then this right here and this right here. So I do everything the same, but now we're starting at pi halves. We're starting here and working our way to pi halves. Okay, so that means that we're going to have negative pi fourths, 0, pi fourths, pi halves. So let's kind of plug in some values here. Okay, let's see here. So let's plug in negative pi halves. Let's plug in negative pi fourths. Let's plug in 0. Let's plug in pi fourths. And let's plug in pi over 2. And let's see what happens at these values. So when I plug in negative pi halves, well, if I go up here into tangent, if I plug negative pi halves in there for cosine, I would get 0. So that would mean undefined. That means in our case, we did it in the previous sections, that we're going to have a vertical asymptote. You know, let me write this better. So we have a vertical asymptote there. And that also means then that I'm going to have a vertical asymptote here. Right? So undefined, undefined, vertical asymptote, vertical asymptote. Okay? And I think they get real picky in your homework. They may ask you to say x equals negative pi over 2 and x equals pi over 2 are vertical. They may ask you to state it. Okay? So just be careful of that. Be on the lookout for that. Now I want you guys to remember that if there's a vertical asymptote, that means that you're approaching positive or negative infinity on the side of that asymptote. So what I want to do is I want to come over here and I want to look. And I already graphed, as you can see right here, I already graphed y equals tan x. And that's what we get. And those little hash marks are pi fourths. Each one of those hash marks is pi fourths. So you can see that it goes through the x-axis at 0, right? Actually, each of those hash marks is pi halves now that I look at it. So as you can see, we go through the x-axis at 0. So let me get this little green. So I'm going to cross here at 0. Now I need negative pi force. When I take the tangent of negative pi force, right? Well, the sine of pi force would be square root 2 over 2. And the cosine of pi force would be, negative pi force would be square root 2 over 2. And we would be in quadrant 4. So that means we would have a negative. So because you have a positive cosine and a negative sine, so you have a negative over a positive, which is a -1. Right? Now, if I plug 0 in there, the sine of 0 is 0 and the cosine of 0 is 1. So this becomes 0. And then pi force should be +1. Okay? So what I'm going to do is I'm going to put these points right here. Now, my drawing isn't super good, so it might be a little deceiving. But what we're doing is we're doing one of these. So that doesn't look very good. It's supposed to look more curved like that. Yeah, so look at the graph on your calculator, and that should make it look a little bit better. Mine didn't come out as good as I wanted. I thought by drawing these extra points. In reality, you guys, the most important thing are the asymptotes and the x-intercept. Those are the most important things. The negative pi force and -1 and 1, those are good because they help you draw a better graph. But in reality, the most important things are the asymptotes, okay? Now, the domain is all real numbers, right? It's every real number that you can think of except for multiples of pi over 2, right? So if you do pi over 2 times 2, that would be pi, which is actually okay. So I think it's odd integer multiples of pi over 2. Let me see here. Pi tangent of pi over 2. Hold on, my brain stopped working for a second real quick, you guys, sorry. So we have pi over 2 plus pi. That would be 2 pi over 2, so that'd be 3 pi over 2. Okay? Now, what if we said pi over 2 plus 2 pi? Well, that would be 4 pi over 2, so that would be 5 pi over 2. And the cosine of 5 pi over 2 is still 0. So yeah, it's all integer multiples of pi halves times pi. So you would say something like this. I think this is how they would want it. The domain is x such that x cannot be pi over 2 plus k times pi. Right? So you could pick kn where k is an integer. Right? Because if you pick k to be -2, oh no, it would have to be pi plus 2, so it'd be 4 pi. So it'd be 4 pi over 2 plus 5 pi over 2. Yeah, so it's k integer multiples, right? Yeah, so, and it's a little bit picky, but if you think about it, it's because you're trying to find, well, where would there be another one? Well, there's going to be another one over here, right? Well, how am I going to get there? Well, that's going to be another pi, right? So this distance from here to here is worth a pi, right? Because it takes a period to recycle itself. So then this would become pi plus pi halves is 3 pi over 2. What would the next one be? You add another pi. That would be 5 pi over 2. Is that right? And 4 pi. Yeah. So you could just keep doing that over and over and over again. Okay. So that's tangent. So let's look at one of these from your book where they want you to do y equals 3 tangent to x. Okay, so what we're going to do is, and this is the domain. So what we're going to do is they're going to ask us to graph it. Okay, you know what, let me write that. Graph using 5 key points, even though in reality, and state the x-intercept and the vertical asymptotes. Okay. Oops. So they're going to say y equals 3 tan 2x, 3 tan 2x. Okay, so what we do first is we're going to build we're going to find our period. So our period is equal to pi divided by omega, which is pi halves, right? So this is pi divided by omega, right? So just keep that in mind. That's where the 2 came from, is omega in this case was 2. So then our interval size is going to be pi over 2 times 1/4, which is pi over 8. Okay. So now what I'm going to do is I'm going to draw my little table. We're going to have x, and we're going to have 3 tan 2x. Now, in general, tangent, I feel like is a little harder to do in your head, so we might have to break out our calculators on this, but we'll see. Okay. The main thing that I always try to do is I try to find the x-intercept. So I want to know when the height of this graph will be 0, and it's not undefined, but when it actually crosses the x-axis. For me, that's a good place to start. So use the x-intercept as a good starting point. That's what I would do. Okay, so let's find our x-intercept. So let's see here. Let's plug in 0 into the function. If we plug 0 into that, that would be the tangent of 0. And when you take the sine of 0, you get 0. And you take the cosine of 0, you get 1. So 0 over 1 is 0. So I know right here that 0 is going to be 0. Okay, so I now have my x-intercept. So now I'm going to draw it. And again, there's no set way you have to do this every time. It's kind of, each one has its own little flavor to it that you may want to mess with differently. So I'm going to do this. Okay. Now I know it's going to cross at 0, 0, right? So I know that the next location is a pi 8 from here. It is going to be a pi 8 away. Wait a minute. Let me see here. So if it has an interval of pi halves, that means that I have to go 3 tan. Did I write this one down correct? 3 tan 2x. So that means that if that is my x-intercept, remember it has to repeat itself. So there should be another x-intercept in another pi from this, right? Or what did we say the period was? The period was pi over 2. Oh yeah, that's why. Okay, yeah, I was confusing myself. So that means it's going to be another pi over 2 from here. So right here would be pi over 2, and there's going to be another x-intercept. And then if I want, I'm going to do another one over here. This is going to be negative pi over 2. That's going to be another x-intercept. So we know that the asymptotes have to go right here. Oops, that looks really off. Oh, I see why it's off, because I didn't draw a very good distance. So this distance from here to here is that much, so it should be one over here. So negative pi over 2. So this is another x-intercept. So then let's do Okay, so these are our asymptotes. And then there'll be another one here. And there'll be another one here. Because I kind of know how tangent function behaves, right? I've seen a few of them now. So the thing is, geez, I can't draw a straight line. So the thing is now, is I know that I have an x-intercept. So if I'm gonna go from here, so this distance from here to here is worth how much? Oops, I'm sorry. This distance from here to here is worth pi halves. That means that I have to have an asymptote at, let me see, what would make that 0? So I need, when would sine of 2x equals 0, right? So sine equals 0 at multiples of pi. So at 0, that would be 0. Oh, I need to find cosine. Sorry about that. I'm thinking about the wrong one. So cosine of 2x would be 0 when? Well, it would be whenever we're at pi halves. Okay, so what would turn this into pi halves is if I multiplied this by pi over 4. So if this were cosine of 2 times pi over 4, what would we get? Well, we would get 0, right? Because this would become pi halves, which would be 0. So that means pi over 4 is going to be an asymptote. Oops, negative pi over 4. And then this will be negative pi over 8. And this will be pi over 8. And this will be pi over 4. Okay? So basically, I had to adjust a little bit because tangent has a different period than the normal sine and cosine. And also with sine and cosine, we normally start at 0. But with tangent, we actually normally start on the left side of it. It's really deceiving my graph. It's really throwing my head off a little bit. I keep seeing it as wrong. So I know that this is what my graph is supposed to do. I know it's supposed to do something like that. And I know right here and right here, this is negative pi over 8, and this is pi over 8. And then this is pi over 4, and this is negative pi over 4. So this is going to be undefined. This is going to be undefined. And then at negative pi over 8, let's see, if we take cosine of pi over 8, or tangent of pi over 8 times 2, that is going to be, let's see here, 2 times pi over 8 would be pi over 4. Oh, so it'd be 3. And this one, oops, this one would be negative 3, and this one would be 3. Okay, because the tangent of pi over 4 is just 1, right? So if I put pi over 8 in here and then multiply it by 3, this is 1, 2, 3. So that would be something like, oops. So let's say we go 1, 2, 3. So that would be pi 8. Oh, geez. You get the idea. It's supposed to be there. I drew my graph a little bad. And then likewise, this one will be somewhere there, but it was supposed to be 3. I just can't draw too good, guys. I'm sorry about that. Okay, so in general, the thing is I already know what it looks like because I've done so many of these. So it kind of makes me guided on how I'm going to do this. Okay, so we end up with something like that. I think I kind of made it look too much like a cubic when it's not quite like a cubic. It's a little bit smoother. So even though the middle one is the ugliest one, it's actually probably the most correct. I couldn't help myself. I ended up drawing them like that. So the thing is, we now know a few facts. Vertical asymptote at x equals negative pi fourths, comma pi fourths. So these are the ones I used, okay? And then we know that the domain, if they ask, would be x such that x cannot equal pi force plus k times pi, right? So all the multiples of that, okay? So that's basically how you do it. It's not quite as nice as the sine and cosine functions, and I always get a little confused when I'm doing them because I don't draw my graphs too accurate, so it can really throw you off a little bit. So maybe try to cut up your line a little bit better than I do when I rush through it. It always seems to throw me off with the asymptotes, but the most important thing is to locate the x-intercepts and to locate the asymptotes, and then from there you can pretty much sketch the graph. All the other stuff is just kind of icing on the cake, okay? So hopefully that, guys, helps you with that one, okay? Cosecant or cotangent, you know what? I don't want to make this video be hours and hours long, so I'm just going to jump straight to a cotangent one. Now remember that the cotangent is, you know what? I think I'm just going to say, you know, that one will be from the homework. I feel like I'm going to end up having like an hour-long video. Unless I can find a quick one that's real nice and easy. No, I don't have an easy one. So I really want to get into the cosecant and secant though, you guys. So let's look at that. We can come back to that cotangent one if you guys want during a meeting or something like that. But it behaves exactly like the tangent function. It just goes the other way. It's like a reflection, and it has different asymptotes because now you have to worry about when the sine function is 0 instead of the cosine function, because cotangent has cosine over sine. But we can go over that in class if you guys like. But I want to get this video done. I don't want to take too long and make this kind of drag out. So what I wanted to do is I wanted to talk to you guys about secant and cosecant. They're basically the same thing. They both behave in a similar fashion. So we're going to say the form of, so we have y equals, or form y equals a cosecant of omega x plus b, and y equals a secant omega x plus b, okay? So the main thing for me on these is you kind of got to be careful and understand that when I show you the guide function is not actually part of the graph. It's just what we use to graph, okay? So let me show you guys real quick what I'm talking about. So let's just jump straight into a problem. So we have y equals 2 cosecant x minus 1, okay? So this actually is right here. Oops. This is a vertical shift. So B, if A is amplitude, B is your vertical shift. Okay, so here's the thing. The key to graphing, sorry guys, there's a helicopter going overhead right now. I'm just going to write for a second. Okay, so the key to graphing secant x and cosecant x functions is to graph sine x and cosine x functions, okay, as guides. So what we're going to do is I'll show you kind of how it works. So we have this graph, and we're looking at y equals 2 cosecant x minus 1. Now what graph is, or what function is cosecant more associated with, sine or cosine? Cosecant is 1 over sine, right? So what we're going to do is we're going to change this to my guide function, of y equals 2 sine x minus 1. And I'm going to graph this guy instead. So I'm going to do everything just like I did in the previous problems from 6.4. And I'm just going to graph this in blue. So I'm going to find my period is equal to 2 pi divided by omega, but omega is 1, so it's 2 pi. Then my interval size is going to be pi halves, right? Because 2 pi, oops, I'll write it out. 2 pi divided by 4 is pi halves. Okay, so I have these. Now I also know, well, we know the amplitude, but amplitude doesn't come as important in these problems. It's not quite the same meaning. So what I'd like to do is I'd like to make my 5 key x values. Okay. So we got x, and we have, oops, I was doing the wrong one. 2 sine x minus 1. Okay. So now 1, 2, 3. Okay. So now what I'm going to do is I'm going to pick my x's, and I kind of already know what's going to happen here, right? I know that I'm supposed to go from here to here, and here's 1, and here's 2, and here's 1, and here's 2. And let's see here. So if I pick my x to be 0, what is sine of x times 2 minus 1 going to be? That's going to be negative 1, right? That sounds right. Now when I pick my x to be, oops, let me cut this up. So just like before, so this should be pi halves, this should be pi, this should be 3 pi over 2, and this should be 2 pi, right? Because we didn't have an omega in this problem to mess with anything. So now what I need to do is find my key x values for y equals 2 sine x minus 1. So I'm going to pick pi halves. And when I put pi halves in here, I'm going to find the sine of pi halves is 1, times 2 is 2, minus 1 is 1. Did I mess that up? So when I plug 0 in here, that's 0, minus 1 is negative 1. Then when I plug pi halves in there, sine of pi halves is 1, times 2 is 2. Okay, I trust that. Now let's plug in pi. Sine of pi is 0, minus 1 is negative 1. Now let's plug in 3 pi halves. So sine of 3 pi halves is negative 1. Negative 1 times 2 is negative 2. Minus 2 is negative 3. And then I'm going to plug in 2 pi, which should be 0. And then times that. So, oops, 2 pi. I feel like I made a mistake, but we can go back. Let me see. Sine of 3 pi halves is negative 1. Negative 1 times 2 is negative 2. Okay, we'll see. All right, so let's plug this in. So 0, negative 1, right there. Pi halves 1, right there. Plug a pi in there, that's 0. That's back to negative 1. Plug 3 pi halves in, that's back to negative 3. Whoa, where did that go? And then we plug 2 pi in, and we're back to negative 1. Oh, I see why. It's just an optical illusion because I didn't draw my graph very accurately. So now here's the thing I want you guys to recognize. These 3 values, right here, here, and here, these 3 values look off a little bit. Like that used to be in the sine function. I didn't graph sines in this graph. But in our previous section, those would have been the x-intercepts. But notice this is our vertical shift. So it took the x-axis and shifted it down -1. So in a way, that's like our new x-intercept. That's like our median line. They talk about this being your median line. Now, it's not actually part of the graph. It's just going to be like a guide for us. Okay. And then I'm going to connect the dots. So now I'm going to go like this, like this, like this, and like this. Okay. So the problem is, what was fooling me a little bit is this distance from here to here does not look even close to as big as this distance, but that's just because I drew it badly. So if you actually calculate this, this is a distance of 1, 2, right? And then this is a distance of 1, 2, right? So it's just an optical illusion. It was throwing me off when I was seeing it. But again, you can always verify a lot of this with your calculator and sketch the graph on there. Okay, so my 5 key X values are over there on the side. But as it turns out, none of this, not a single thing that I drew, is actually part of the graph. Oops. So in order to draw your secant function, anywhere that would have been considered an x-intercept, that would have made the sign 0, you have to make that an asymptote. So I'm going to put an asymptote here. I'm going to put an asymptote here. And I'm going to put an asymptote here. And the reason for that is remember that we're dealing with cosecant. We're dealing with cosecant, and cosecant is 1 over sine. So whenever the sine would have been 0, we then have to say that's an asymptote, because you can't put a value in there into the cosecant function. Well, the sine function would have been 0 anywhere that we got -1 as our answer, because that meant we did 0 minus 1. So it's in those 3 locations. And then on top of that, that's still not the graph. Now what I do is now I take, and everywhere right here, oops, don't do that. Uh-oh, what's happening, guys? Okay, thank goodness. All right, so everywhere, so I'm going to start here, and I'm going to draw this little, like almost looks like a parabola, but it's not. And then I'm going to draw this one here. And then right here where there's a local min or local max, I'm going to draw this. Okay. And as it turns out, that is the only part of my graph that you actually see. So all of that stuff that I had drawn in blue, that was just to show me the guide. And wherever there was a maximum or a minimum, a peak or a valley, you draw this like parabola looking thing facing the other direction. Okay. Does that make sense to everyone? So hopefully you guys can see that there used to be this blue graph, right here. Let me see, before I erased it. That blue graph was right there, right? That actually is not even part of what we're trying to do. All of that is just to give us a guide on how to draw that stuff in green. So now I erase all of that. And then I erase this fake x-axis, because that's not real either. And now I have these 2 blue graphs, or these 2 green graphs. This is the only part of the graph that's actually exists, right? And I mean, then we can draw a whole bunch of them. But if we want to just draw one period, this would be one period from 0 to 2 pi, okay? And as you can see, the domain is from 0 to pi, and then from pi to 2 pi, right? So if you're just doing one period, it's like that. And then you could say that you have vertical asymptotes, because sometimes they want to know vertical asymptotes. So this is the graph of y equals 2 cosecant minus 1, okay? And we have vertical asymptotes at x equals 0, x equals pi, x equals, oops. x equals 2 pi, okay? And vertical asymptotes would occur at all multiples of pi, okay? Because that's what would make sine 0 in the denominator, okay? So these are a little bit trickier because you have to graph another graph first and then get rid of it and then go back and graph this. But it still basically is based on secant and cosecant are still based on sine and cosine, okay? I think that's gonna do it for this video. So you guys can kind of get started on these. 6.6 is the harder section. 6.6 deals with all of this now, with vertical shifts, horizontal shifts, amplitudes, you know. Oh, that was one thing. In general, we kind of don't talk about amplitude with tangent and cosecant and secant because they go on forever. And remember, amplitude is the distance from the median line, so it's kind of not something that's applicable in this sense. So it did affect everything, and it definitely affected the amplitude of the guide function. So the guide function had an amplitude equal to, the absolute value of A, which was the absolute value of 2, which equals 2. So that means from the middle line, the median line, we had to go up 2 and down 2, which is what we did. That's why when the median line got shifted to -1, if you go down 2 from -1, you get to -3. And if you go up 2 from -1, you get to +1. And that's why you see that's where the graph starts at -3 and 1 with our little like fake parabolas, okay? All right, you guys, that's going to do it for this video. Be on the lookout for the 6.6. That kind of is like, now that you know how to do all this, let's just do a bunch of the harder versions.